Yeah, that actually woke me up because we have like rose bushes by like the windows, and they
Oh,
started smacking on my bedroom
oh
window
man.
because it's on the first floor. And I was like, okay, thank you.
Yeah, we have a big tree that's like right next to my window at home. And so yeah, it was just smacking my house just all night.
I'm curious, how do they determine what 500 level classes to offer? It doesn't really matter too much to me right now, but I'm
Mhm.
just curious because they have very limited options each semester.
Yeah, that's definitely the big criticism in general of the five medical courses. Honestly, we have a few that's in our catalog, and we try to rotate them so that we offer them once every 3 or 4 semesters.
Okay.
And so they're just kind of on a rotation right now. We kind of have a chicken and the egg problem with our grad program right now. Where like, we the big complaint that we get from students that we don't offer enough grad courses, but in order to offer more grad courses, we need more students. Because the school is very strict in terms of like if you don't have at least this many students in your class, then we're going to cancel it, or we're just not going to give you money for it. But then to attract more students, you need to offer more classes. But to offer more classes, you need to have more students. And so, yeah, it's definitely been a challenge with that.
One of my bosses for SI that he got his master's in chemistry here. He said he had a class. He was the only student in it for his master's. That he managed to convince them to still run it because he needed it for his like specific concentration,
Yeah,
and it had
yeah,
never been offered in like any other semester.
yeah, yeah,
I was
yeah.
like, that is such a terrifying.
It was a different time back then. There was yeah. I different time, probably different school too. Yeah,
Well,
that
here,
would never.
I've got it
Oh, here.
here. Yeah, it was like probably 4 or 5 years ago.
Oh, wow.
Yeah, then he said, he begged the chemistry department and the teacher to still run it because he
Yeah,
needed it for his concentration. And I
yeah,
said, yeah.
yeah. That's very hard to do today. Honestly, as instructors, those are the most fun classes too. When you don't have that many students, you can really kind of dive in and kind of really get a lot of good interactions. But yeah, they have bills to pay, I guess, or they have president salaries and provost salaries to pay, so they can't we can't offer that.
I do think it would be very funny to have an exam in a class like that.
Yeah. Usually for such small class like that, you would have projects, not exams.
That's generally what he said.
Yeah. Yeah, we're still working on it. So right now, we're kind of at the stage where we're trying to making sure all the required courses have staffing for them. Um, and we're gonna see who's available after that to teach electives. So we're definitely gonna add more. So I anticipate maybe like 6 or 7 more electives are probably gonna be added. But because the electives are they're so specialized that most electives only have one instructor that can teach it. And so it just depends on who's available after all the required courses. So then we'll post it after that. I did request two. So I requested to teach 417. So 417 is computational heat transfer. So it's kind of like a MATLAB heat transfer class. And then I also asked to teach 442, which is cardiovascular flow. So it's kind of almost like a follow-up to this class, but for blood flow. Yeah. But we'll see if I get them because I know for sure 540, it's a grad course. I think I'm most likely going to be the instructor for that course. And then I do advising, and so that leaves me only 2 other courses. So yeah, we'll see. Yeah. Mhm. All right, it's 4 o'clock. Let's go and get started. Oh. Question in the chat. Let me see. Posting lecture notes from yesterday's optimization class. They are up. They should be up online. I'm a little bit behind on posting the lecture. So and I think I haven't posted the notes or the lecture video from Monday too for this class. So I'm gonna go do that in my office when I get back. But the notes from yesterday should be up on Canvas for the week 11 page. Yeah. Okay. So it's Wednesday, week 11. How's everyone doing this week? Hang in there, right? Okay, so today we're starting something new. So we are starting the topic of inverse dynamics. So inverse dynamics, now that we kind of are finished with human motion kinematics, now it's time to kind of put that it's Wednesday, my dude. Yeah, that's an old meme. That's I'm old enough to remember that one. Now that we've gone through kinematics, now it's time to put that data to work and compute forces, right? Because ultimately, even though we're doing motion studies now, ultimately we're interested in the same quantities that we were studying in static analysis, which were muscle forces and joint reaction forces, right? It's just going to be a lot more complicated to do that because in motion things move, and so we're going to talk about how to do that today. Basically taking the data that we got from human motion kinematics, putting them into our equations of motion, and then using that to compute our forces. Okay, so compared to human motion kinematics, this section here is not that much new. It's basically the same equations of motion that we studied in the first half of the class. The only difference now is that when we sum the forces, they're not going to be equal to 0. They're going to be equal to mass times acceleration. Okay. So this section should go a lot faster than the previous one. We spent quite a bit of time on human motion kinematics, but we should be done with this one. We should be done with this section by, well, Monday we have off, so we should be done with it by next Wednesday. Okay. All right. So announcements. So hopefully everyone got my email before the class, and so we talked about the final project on Monday. So make sure you guys are thinking about the groups that you want to form. And so as soon as you guys have a group of 3 to 4 together, make sure you just let me know. Let me know the topic that you want to run, and just so I can reserve it for you, just so that you can start researching it. Okay. Because once Thanksgiving hits, the semester is going to go pretty fast. And so, we're going to have Thanksgiving. We have 1 week of class right after Thanksgiving, and then we're going to launch right into final presentations from there. So, not too much time from here on until the end of the semester. Okay. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and start. Okay, so we're starting a topic called inverse dynamics. Okay. Okay, so what is inverse dynamics? So now that we have a way to measure and quantify the kinematics of human motion, we can now use that information to compute forces and moments and torques and things like that. Okay. Okay. So forces and moments are the goal. Specifically, muscle forces and joint reaction forces, that's the ultimate goal of our analysis, right? So why do we call it inverse dynamics? It's kind of a weird kind of name. Kind of sounds like something out of a video game. But the reason we call it inverse dynamics is that it's kind of different from, I would say, kind of traditional dynamics. And so, in traditional dynamics, usually in the problem, you're given some kind of forces or moments in the problem, and then you use those forces and moments to compute the motion, okay? So in normal, all right, so that's probably what you're probably used to in your previous dynamics courses, right? Of course, now we're doing the opposite. And so now, we're given the motion. So we're given the human motion kinematics data, and we're going to be using that to compute what forces and moments cause this motion, okay? So that's why we call it inverse dynamics. And so kind of an interesting kind of a way to do it, okay? Okay. So ultimately, we want to compute, or we want to predict the muscle forces okay? Ultimately, we want to compute muscle forces, right? And so it's kind of the same as kind of static analysis, right? Because once we have muscle forces, that's usually kind of the most interesting thing from a biomechanics point of view. Just because, if injuries occur, usually we can predict that with the muscle forces. Maybe there's a particular muscle that's exerting itself a lot, or maybe we can use it to help design, biomechanical equipment, okay? So, you would think that using inverse dynamics would get us this information, but it actually doesn't. So, we actually need to learn one more topic before we can actually get ultimately to the muscle forces, okay? And so the three steps to a typical kind of motion study are the following. So we've done the first step already. So the first step is some kind of motion capture analysis. This gives us the kinematics of the motion, okay? So we've gone over that the last couple of weeks, and so we kind of understand that in very good detail now. Number two is inverse dynamics. Okay. So that's what we're going to be doing this week. And so from inverse dynamics, we're going to be able to obtain the net forces at all the joints, net forces and net moments at all the joints that cause the motion. Okay. So that term right there might be a little bit kind of vague at this point, but as we kind of go through the lecture today, you'll kind of understand what that really means. Okay. And then the last step, which will probably be the last topic that we go over together in this class, is muscle force optimization. Okay. For those of you that are in both this class and my 454 class, it'll be kind of a surreal moment to kind of see optimization in here. But this is, I think, one of the most practical uses for optimization as well. So you have kind of a problem that is under constrained in a lot of ways, and so you have to use optimization to solve for that problem. Okay. And by under constrained, what I mean is, for most motions in the body, usually you're going to have multiple muscles contributing to a particular motion. And so, even just a simple motion of just, doing a bicep curl, right? We've already seen that there are, at least 3 muscles in your upper arm that contribute to a bicep curl. So how much work each particular muscle does, you need some kind of optimization algorithm for that. Okay. And so what you get from this are the individual muscle forces. Okay. All right, so that's kind of the three-step process that we're going through. And so of course, right now we are on step 2, but eventually, we're going to get to all. Okay. Okay. Any questions on this so far? Okay, good. All right, so before we start talking about kind of the methods itself, we need to talk about some measurement techniques. Okay. Okay, so good. So to do a proper kind of inverse dynamics analysis, not only do you need the kinematics, so at this point we're going to assume all the kinematics are done, but we also need a way to quantify and measure any external forces that are acting on the human body. Okay. All right, so there's lots of different ways that we can measure external forces, and so an external force, it doesn't have to be from some external agent. A lot of times, it's just something as simple as just the normal force that the ground exerts on the body. Okay, so one popular method for measuring this, and we've mentioned this before. We mentioned this when we were talking about gate biomechanics, is the idea of a force plate. So force plates are great for measuring ground reaction forces that act on the human body. Okay. And so just to kind of remind you what a force plate is, it's basically just like a very small scale, or it's not a small scale, it's a large scale that you stand on, and it's able to measure forces on it, with very sharp precision, and that can change very rapidly as well. Okay. So may look something like this, some kind of plate, right? There may be some kind of load sensors right underneath. Okay. And as soon as someone steps down on this, the force plate is able to measure the ground reaction forces that come up. Okay. All right. So that ground reaction force is really important, because that ground reaction force, this is going to be used in our inverse dynamics analysis. So, what you're going to see is that inverse dynamics is kind of a couple things. And so one thing is that, we're going to be setting up all of the equations of motion, but to kind of stimulate the equations of motion, you need to be able to apply some kind of external force. Because without external force, the equations of motion are just going to be, not really much by themselves. Okay? Okay. And so you have to have some way to measure that. And so whenever you're doing lower body biomechanics, force plates are often used for that. But you can come up with other ways to measure input forces as well. Okay. All right. So let's go through the analysis. And so let's go through the steps and what's involved with an inverse dynamics analysis. Okay. All right. And so, the goal for an inverse dynamics analysis is to be able to compute the net forces and net moments that have to occur at the joints to cause a specific motion. Okay. And so if you have a person's body here, so let me go ahead and kind of draw an example for you. Okay. So let's say that we have a person that's kind of doing a squat. Okay. He has a really big foot for some reason. Okay. Okay. So I have three joints here. So I have we have the ankle here, we have the knee joint, and then this joint here is the hip. Okay. All right, and so let's say that this person is kind of mid squat. So he's about to kind of, he's either squatting down or he's about to kind of pop up. Okay. So to cause this motion, one way that we can kind of quantify the forces is that we can say at every single joint, okay, so for the ankle joint, we have FAX, FAY, and we also have a moment applied there as well, MA, okay? At the knee, we have FKX, FKY, maybe MK, okay? And at the hip, we have everything as well. So FHY, FHX, and MH, okay? So these are not, remember, these are not muscle forces per se. These are all the forces and moments that have to act at the joints in order for us to cause the motion. Okay. Remember what a net force is. And so a net force, whenever we say that a force is net, usually it's a result of a combination of multiple forces. Okay. And so, usually, for any kind of, body here, right, we may have several forces acting on it. So we have F1, F2, F3, okay? Right? So to simplify things, we usually we can add all these forces together. So maybe our net force, looks something like this. Okay. So we basically sum up all the contributions from all the individual forces, and we just have one force acting at that point. Okay. These net forces are the same. So these net forces that we're going to compute in inverse dynamics, these are all from the contributions from all the muscles in that area. Okay. So, I want to make that really clear that, these net forces, eventually we're going to use these net forces to compute, the individual muscle forces, but we're not quite there yet, right? And so in order to get to that point where we can compute individual muscle forces, we have to start with the net force. And then from the net force, we compute the muscle forces through optimization, okay? So, this whole process of doing motion analysis, it's really kind of backwards when you think about it compared to, your usual way of solving these types of motion problems. Because usually in a motion problem or in a dynamics problem that you may have had in a previous class, you're given all of the individual forces, right? So you're given all the forces, and then the first step that you would do is you would sum up all those contributions and you would get a net force. And then from that net force, you would then compute the motion, okay? We're basically going the exact opposite direction from all that. So we're starting with the motion. We're using that motion to compute the net forces, and then we're going to use the net forces to compute the muscle forces, okay? So you kind of have to kind of flip, I think, the usual paradigm that you usually kind of think of when you think of, mechanics type problems, okay? And so we'll kind of see how that kind of goes. Okay. All right. So to perform an inverse dynamics analysis, you need a few different things. Okay. So these three things are the inputs to an inverse dynamics analysis. Okay. All right. A, just because I've done quite a few numbered lists, and so I don't want to overlap them. So A here is going to be some kind of representative model for the subject. Okay. So we have to be able to represent kind of the human body in some way that's useful for us to perform analysis. Okay. Usually the model that we're going to adopt here is kind of the same model that we've always adopted for this class, is we're going to break up the body into different body segments. And each body segment, while they are interconnected with each other, each body segment behaves as kind of a rigid body. Okay. So that's our typical body segment approach. Okay. All right. B. Next thing that we need the motion kinematics as a function of time. Okay. So we need to be able to have the joint angles, the joint accelerations, joint velocities, angular velocities, angular accelerations. So we need to be able to have access to that data for our given subject. And of course, with the way that we obtain this is through motion capture. Okay. And then C, the contribution that we just talked about, which is measurements of any external forces on the subject. Okay. So once we have all of these established, the way that we do inverse dynamics is we basically write out our three equations of motion for each body segment. Okay. And so that means we're going to do the sum of the forces in the x direction, sum of the forces in the y direction, sum of the forces in the, or excuse me, we're only doing 2D problems. Okay. And so we're going to sum the moments as well. Okay. We're going to do the sum of moments a little bit differently. And so when we sum the moments here, we're actually going to sum the moments around the center of mass of the whatever body segment that we are analyzing. Okay. All right, and you'll see kind of why that's the case in a bit. Okay. And so the sum of the forces in the x direction, before in static analysis, we would set this equal to 0. But in dynamic analysis, we're saying this is equal to mass of the body segment multiplied by its linear acceleration in the x direction. Okay. For the sum of the forces in the y direction, we are setting it equal to mass times the linear acceleration in the y direction. Okay. All right. And then for the sum of the moments, we're going to set that equal to the moment of inertia of the body segment multiplied by its angular acceleration. Okay. So this I here is new. We haven't seen this I before, but remember this is a moment of inertia. Okay. So it's new relative to this class, but hopefully you're familiar with the concept of moment of inertia from the previous courses. Okay. All right, and then to this you add one extra term. And so to this you add a vector cross product. So we have R P cross with m times the acceleration vector. Okay. Okay. So that last term there may or may not be familiar to you, depending on dynamics. It's actually been a lot of years since I've taken dynamics course. Okay. But this last term here, this last term is to account for the fact where, if you were to sum the moments around a location that's not the center of mass. Okay. And so if you were to sum the moments around a point that is not the center of mass, there's some additional contributions that you have to account for based on kind of the inertia of the part itself. Okay. And so this RP here, right? This vector in particular is a vector that points from the center of mass of the body segment to whatever location that you are summing the moments around. All right. So, to be kind of perfectly honest with you, that last term there is kind of a pain in the butt to evaluate just because of the cross product. And so to save ourselves the headache, if you sum the moments around the center of mass, you may have some extra contributions just because you have forces. You have a lot of forces that are contributing to the moment. But if you sum your moments around the center of mass, then that last term there is going to go to 0. Because that RP vector there is going to be 0. Because if you have a vector that goes from the center of mass to the center of mass, that's basically a 0 vector right there. Okay. And so to save ourselves the trouble of computing this, so if you're summing the moments around the center of mass, okay, then this term goes away. Okay. So most of the time, we want to kind of ignore this, but I'm just making you aware that it's there. And so, that's kind of the reason why we have to sum the moments around the center of mass. Because it's going to be tempting because it's a little bit different than how we sum moments in static analysis. And so in static analysis, if you remember, whenever we sum moments, we sum them around the joint itself. That's to kind of save us some time in terms of, the amount of terms that we have to compute. But in static analysis, it didn't really matter because, both of these terms here were 0 in static analysis. But when you account for motion, you have to make sure you account for that extra term right there. Okay. But we don't have to account for that extra term if we sum it around the center of mass. Okay. Any questions on this? Okay. And so of course, to obtain these equations, we have to draw our free body diagrams for each segment. Okay. So we're going to be going back to doing that. And so we're going to be drawing basically free body diagrams, writing out the equations of motion, and using that to solve for forces. Okay. Okay, because again, like what's different from traditional dynamics analysis, usually when you do dynamics analysis, you're solving for the quantities here on the right-hand side, right? So you're solving for the accelerations, you're solving for the angular accelerations. But now, in inverse dynamics, these quantities are going to be given to us. Okay? And so what we're actually going to be solving for, the unknowns in our equations are actually going to be on the left-hand sides of these equations in the force summations. Okay. All right, and so once we kind of start doing an example, you'll kind of see how this is. Okay. All right, so let's go ahead and jump into an example. No time like the present to kind of do this. Okay. All right, so in this example here, let's do an inverse dynamics analysis of a squat. Okay. And so in particular, we're going to focus on all of the body segments in the lower extremity. Okay. So that is the foot, the lower leg, and the thigh. Okay. That means we have 3 joints to consider as well. So we have the ankle joint, we have the knee joint, and the hip joint. Okay. Okay. All right. So let's go ahead and draw the figure here. And I'm just going to draw it as a stick figure. Okay. So this would be kind of the weirdest looking person that you'll probably ever see. Okay. All right. So this is what we have here. So this is at the bottom here, we have the foot. Okay. Our foot is our little triangle right there. Okay. This segment here is the lower leg. And this segment here is the thigh. Okay. All right. So this joint right here, this is our ankle joint. This right here is our knee joint. And this right here is our hip. Okay. Okay. So let's go ahead and draw some dimensions here. So we are aware of all of the lengths of these segments. Okay. The foot we're going to mostly ignore, or in other words, we're going to say that the foot is kind of relatively small compared to everything else. But for all the other body segments, we know their dimensions. Okay. Okay. So let me go ahead and draw that in green here. Okay. So first thing for the lower leg, the distance between the ankle joint and the center of mass of the lower leg. Okay. So this green dot right here is the center of mass. And so we're going to say that is R1. Okay. We also know the properties of the lower leg itself. So we know its mass and moment of inertia. Okay. We also know the total length of the lower leg as well. So the total length of the lower leg will be L1. Okay. So I think in the past, we've kind of made the assumption that the center of mass is usually in the middle of the body segment. We're kind of breaking that assumption at this point. So we have two separate variables, R1 and L1, to differentiate between the location of the center of mass and the total length of the segment itself. Okay. We have the same information for the thigh. And so for the thigh, we have the center of mass. And so we'll call that M2. We know its moment of inertia, I2. Okay. And then relative to the knee joint, the distance from the knee joint to the center of mass of the thigh, we'll say is R2. And then the distance from the knee joint up to the hip joint, so the total length of the thigh, it will be L2. Okay. Okay. So just because the figure's getting a little bit crowded, I'm going to start writing on the side here. Okay. Another piece of information that we know is we know all of the joint angle kinematics from let's say we got them from a motion study. Okay. And so at the ankle, let's say at the ankle, we know the joint angle of the ankle. We know the angular velocity at the ankle, so that's omega A. And we know the angular acceleration, alpha A. Okay. At the knee, we also know all those quantities. So we know its joint angle theta K, its angular velocity, omega K, and then its angular acceleration, alpha K. Okay. At the hip, we have all the same quantities. So we know its joint angle, theta H, omega H, and alpha H, angular velocity, angular acceleration. Okay. So all are known from motion capture or motion study. All right. Last piece of information that before we actually start solving this, we need to have some kind of external force that's acting on this the structure. Okay. And so the external force in this case is pretty obvious, just because in order to hold itself up, there needs to be a normal force acting from the ground, and that normal force is going to be our external force. Okay. So we have a normal force Fg. For Fg here, this is the normal force that the ground exerts on the person. Okay. Good. So a lot of information, a lot of variables to kind of keep track of here, but you'll see that once we start writing the equation, once we start writing the equations, everything will kind of fall into place. All right, any questions on just the setup for the problem, just the diagram here? Okay, good. So now that we're given all this information, let's write out the objective for the problem. And so what we want to do is we want to compute the net forces and net moments at each joint of this figure. Okay. Okay, so very, very typical kind of inverse dynamics type problem here. Okay, so we're given the diagram, we're given all of the dimensions of the diagram itself, all the lengths, all the angles. We have its motion kinematics as well. So we're assuming that we know the angular joint angles, angular accelerations, angular velocities, and we have some external force as well. Okay. And we basically want to translate these to joint angles, or excuse me, joint forces and joint moments. Okay. Okay, so let's start. So the way we're going to do this, and the way that we perform inverse dynamics analysis, is we're basically going to be drawing free body diagrams for every single segment of this figure here. Okay. So we have three segments to consider here. So we have the foot, we have the lower leg, and we have the thigh. Okay. So the first question we have to ask is, which one do we start with, right? Eventually, you're gonna write free body diagrams for all of these parts, but you got to know where to start. So my general advice, just to kind of make things easier for your calculations, easier for your logic, is to start with the body segment that is being acted upon by the external force. Okay. You don't have to. You can start from the other end if you want. You could start from the middle if you want to, if you really want. You're going to be solving all of it in the end eventually, but it kind of helps to make kind of more logical sense if you start with the where the external force is being applied. Okay. At least for me, logically it makes sense to kind of start from kind of the most external part of your body. That's usually where the external force is being applied, and then kind of work your way inwards from there. Okay. Okay. So let's see which body part kind of fits that criteria for this problem. Okay. So the body part here that's being acted upon by the external force, there's only one external force here, which is the ground reaction force, which is the foot. Okay. Okay, so let's start with the free body diagram of the foot. Okay. And actually, the foot is actually a really convenient body part to start with here for this specific problem. Granted, this is not always going to be the case for the problems that you do, but it just so happens here that the foot is also stationary. Okay, so if you look at someone doing a squat, right? You'll see that their lower leg and their thighs are going to rotate as they go through the squat. Meanwhile, the foot kind of stays planted on the ground. Okay, and so this is actually a body part that's actually going to be stationary during the motion. Okay. So that means AX is equal to AY is equal to alpha, and they're all going to be all equal to 0. Okay. So essentially, if we start with the foot here, we can basically treat it like a static problem, which is pretty nice. Okay. Okay. So let's go ahead and draw the foot. Okay. So we're going to draw a free body diagram of the foot. So I'm going to draw it as a triangle here, just to make things a little bit simple. Okay. Up here we have the ankle joint. Okay. We have the ground reaction forces coming from the ground, and we're going to assume that the ground reaction forces are acting at the toes of the foot. Okay. So FG. Okay. So this right here is the toes. Okay. All right, another thing that we're going to need, let's go ahead and input the length of the foot itself. So this wasn't given in the original diagram, but we needed to complete the free body diagram for this part here. Okay, so let's assume that the distance from the toes over to the ankle, the horizontal distance, is given by an amount L. Okay. Okay. So that's everything that we know so far. The other thing that we know here is that at the ankle, we're going to be having joint reaction forces. Okay. So we have, we'll call it FAY, FAX, and we also have a moment as well. Okay, so we have a T1. So well, let me just group these guys. So everything in blue here, these are the net forces and net moment at the ankle joint. Okay. And these are unknowns. Okay. And so ultimately, when we write out the equations of motion, we're going to solve the equation of motion for these variables here. Okay. Okay. All right. So let's go ahead and sum up the sum up the forces and moments here. Okay. So first we have the sum of the forces in the x direction. So when we sum the forces in the x direction, you can see we only have one contribution here, which is FAX. Okay. Actually, it's a negative FAX, so it's going to the left. Okay. Ultimately, it doesn't matter if the negative there, just ends up being 0 anyway. Okay. All right, so we set this equal to the mass times the acceleration of the foot itself. But what we know from the foot is that the foot is stationary. Okay. And so since the foot is stationary, we know that the acceleration is equal to 0. Okay. And so we can actually solve this equation outright first. And so we can say that FAX is equal to 0. Okay. Okay. Now we have the joint reaction we have the sum of the forces in the y direction. And so in the y direction, we have two contributions here. So we have FG, right, going upward. So it's going to be a positive contribution to the sum of the forces in the y direction. And then we have a minus FA, comma y. Okay. So that is equal to the mass multiplied by the acceleration in the y direction. We know the acceleration in the y direction is equal to 0. Okay. And so what this tells us is that FAY is equal to FG. Okay, good. All right, and so the last equation that we have here is the sum of the moments. Okay. Now, remember what I said before that, usually when you sum the moments in these situations, you want to sum the moments around the center of mass. Okay. It turns out, for this particular problem, it doesn't quite matter anyway, just because the foot is stationary. Okay, so let's go ahead and sum the moments around a convenient location. Okay. And so let's do what we usually do for our static analysis, and let's sum the moments around our joint. Okay. All right, but I'll go ahead and leave a note here. So since foot is stationary, does not matter where we sum the moments. Okay. And so for stationary cases, let's just choose something convenient. And so one thing that's convenient is the angle, because that eliminates FAX and FAY from the equation, so we don't have to worry about them. Okay. Okay, so we sum the forces, we sum the moments around the ankle, excuse me. Okay. So let's do our usual kind of moment equations here. And so we have one contribution from the external force Fg. Okay. And so if we do what we usually do, our Fg here is a vertical force. And so its contribution to the moment will be the product of the magnitude of the force Fg multiplied by its moment arm. Okay. And it turns out our moment arm is very conveniently given to us there as the length L. Okay. And we see based on this that it is a clockwise contribution. Okay. And so that means we're going to have a minus Fg multiplied by L. Okay. All right, so that's the first contribution to the moment equation. The other contribution to the moment equation here is you can see we have a moment or a point moment that's applied at the ankle itself. Okay. So don't forget this. And so it's very easy to forget this just because we didn't account for this in our static analysis, but don't forget to add the point moments into the moment equations. Okay. Okay, so our point moment here we can see is T1. And so the way to add point moments are, if you've never kind of seen them in in an equation before, they already have the units of moment to them. Okay, so unlike a traditional force, you don't need to multiply the point moments by any kind of distance because it's already in that form. Okay, and so for this one, the only thing you have to worry about is just the sign. Okay? And so for T1 here, we can see T1 is also going in the clockwise direction. And so we have a minus T1 into our equation here. Okay. All right, and so this is equal to I times the angular acceleration plus RP cross product MA vector. Okay. But we know that the angular acceleration is 0. We know that the linear acceleration is 0. And so this whole thing's equal to 0. Okay. And so what this tells us is that T1 is equal to minus Fg times L. All right, and so that's our first segment. Okay, so we're able to compute the net forces and the net moment applied at the ankle joint, for this motion here. Okay. All right, any questions on how we got these results here? Okay, good. So you can see here with inverse dynamics, it's not as foreign as human motion kinematics, right? So these are things that we've done dozens of times in this class before, and so it's just applying them with motion now. Okay, but this first one, honestly, was just kind of a warm up. We didn't actually account for any motion here just yet. Everything was static here. So let's move up to the lower leg. And so we can do kind of our first real kind of inverse dynamics. Okay. Okay. So we're gonna draw our free body diagram of the lower leg. Okay. Okay. So let's go back up to the figure here. Okay. Just to make sure I draw the leg in the right orientation. Okay, so I'm going to use just a line here to represent our lower leg. And unlike the figure above, I'm going to make it big so we can see all of the contributions here. Okay. Okay, so first thing we have, let's go ahead and make note of the center of mass. Okay. So center of mass is going to be right here. Okay. So that's M1 and I1. Okay. Remember, this is located at a distance of R1 from the ankle joint. And the entire leg itself has a distance L1. Okay. Okay, so first thing we note here is that because this body segment has mass, there's going to be a gravitational force acting on the part. Okay, so we have a gravitational force. Its magnitude is is M1 times G. Okay. Right. So the weight of the segments themselves are going to contribute to this. Okay. Then and besides that, there's no other external forces, and so that's the only kind of external force that you can say, which is the weight. Okay, all of the other forces that we have applied here are going to come from the net forces at the ankle and the net forces at the knee. Okay, so remember, down here is the ankle joint, right? And so we have net forces that are being applied from the ankle joint here. Okay. And so actually, we've already computed these. Okay, so it's FAX, FAY, and T1. Okay, so we just need to apply them here. Okay. Okay, so for FAX, we have it going in this direction. FAY is going to be in that direction. And then T1, we're going to say is in this direction. Okay, so everything that everything that's down here, we computed these in the previous step. Okay, so they're not unknowns, so we know them. Oh, question, yes.
Do we need to show the FAX in this case because it's 0?
Yeah, so technically it is 0 here, but I'm just kind of showing you this for completeness. Yeah. Mm-hmm. Mm-hmm. All right, so we computed these in the previous step, but if you look a little bit carefully here, so if you look at the directions that I chose for each of these vectors, they're actually very intentional. Okay. And so what do you notice? And so let's look at FAX first. And so in this free body diagram of the lower leg, you can see we have it pointing to the right. Okay. But the way I drew FAX up here at the foot, you can see that it's pointing to the left. Okay. Same thing for FAY. So FAY here at the foot, I originally drew it going down, but then when I move to a different body segment, I'm instead pointing FAY going up. Okay. Same thing with T1. So for the net moment here, in the first diagram, I'm having it go clockwise. And then in this diagram here, I'm having to go counterclockwise. Okay. So whenever you do free body diagrams of neighboring body segments, the net forces that you previously computed at the joint, those are going to carry over to the next body segment. They're going to have the same magnitude, but their directions have to be reversed. Okay. Okay. So you want to be careful with that. So you want to make sure that you draw those correctly. Okay. And the reason that they're opposite is kind of just goes back to Newton's third law of every force has an equal and opposite reaction force. Okay. So since we're looking at kind of a neighboring body segment here, then those same forces that were acting on the foot, those same forces are going to apply forces on the lower leg as well, except they're just going to be opposite in direction. Okay. Okay, but for all intents and purposes, besides the direction swap, we know these already. Okay. Because that's really good, because we're going to have unknown forces at the knee. Okay. Okay, and so at the knee, we can go ahead and draw the forces there as well. Okay. Okay, so at the knee here, we have FKX, we have FKY, and then we have T2 going in the clockwise direction. Okay. Okay, so now in this body segment here, these three forces, the two joint reaction forces and the joint moment at the knee, these are now going to be the unknowns that we're going to solve for. Okay. Now, does it matter, which directions that you draw your reaction forces, right? So you can see for this problem, I'm kind of going by the convention where, the first time that we draw the joint reaction forces and the joint moments, I'm drawing them all in their canonical negative directions, right? And so if we look back at the foot, when I first introduced the ankle forces, I drew them in the negative X direction, negative Y direction, and a clockwise moment, okay? Same thing for the lower leg. So, this is the first time that we're seeing the knee forces. And so I'm drawing the knee reaction force to the left, down, and clockwise, right? So it doesn't matter. Do you have to do it that way? No. I mean, you can, you can very easily draw these reaction forces going the opposite direction, as long as you're consistent with the directions in the next segment, okay? So, if you were to kind of redo this problem where, instead of having these go this way, you have them go this way. Okay. So we kind of draw everything going in their positive directions. That's fine too. The only thing is that when you do the free body diagram of the thigh, which is the next segment, you draw them in the opposite directions. Okay. So, the choice of initial directions doesn't really matter all too much, as long as you're consistent and you carry that through, for all of the analyses. Okay. All right, but for this one, I'm just going to go back to the way I had it before, just because my notes are like this, and yeah, don't want to do too much thinking right now. Yeah.
Would it have been worth it to reverse the direction of T1 on that first part because it was already negative?
It would, yes. And so if you kind of knew ahead of time, so you kind of have a lot of negatives here. You're right. So the fact that we got a negative answer for T1 means that on this diagram, T1 is actually going in the opposite direction. And so if you want to keep the magnitudes positive, you can do that, and then redraw this one as going the opposite directions too. So just kind of make sure you're kind of consistent with everything. Yeah. Okay. So let's go ahead and write out the equations of motion here. Okay. Okay. Keeping in mind that this body segment is not going to be stationary, and so we're going to have non-zero values for the accelerations. Okay. All right, but we'll cross that bridge when we get there. All right, so first we have some of the forces in the X direction. And so let's sum up all the forces that we see in the X direction here, okay? So we have two forces that are shown here. Of course, one of them is 0. We know that FAX is 0, but let's include it in the free body. Let's include it in the force summation just for now, okay? So we have a positive FAX, and then we have a minus FKX. Okay. This is equal to the mass of the segment, which is m1, multiplied by the linear acceleration in the X direction for this body segment. Okay. Okay, I'm going to leave it at that for now, just because computing the linear accelerations is actually a little bit of an ordeal. Okay. Okay, next we have the sum of the forces in the Y direction. And so we sum up the force in the Y direction. We have three components here. So we have the contribution that's coming from the ankle. So it's FAY, okay? we have the gravitational force. So don't forget the gravitational force. It's easy to kind of forget that. So we have a minus m1 times g. And then we have the contribution from the knee. And so that's going to be minus fky. Okay. And this is equal to the mass times the acceleration in the y direction. Okay. All right. And then finally, we have the sum of the moments. Okay. Now, we do have motion here. And so, we have to be a little bit careful about where we're summing the moments. And so since we have motion here, the most convenient point is going to be to sum the moments around the center of mass. Okay. Now, this means that we're going to have a lot of terms here. So we're going to have a lot of, basically each reaction force or each net force at the joints, FAX, FAY, FKX, FKY. All four of those are going to contribute to the moment, as well as the point moments, T1 and T2. Okay. But it's worth it to not have to do that cross product. And so, but it's up to you. If you're okay doing a cross product, you can sum the moments around the ankle joint and just kind of deal with it that way. There's a saying that we have in science where it says, there's no free lunch. And so, there's a lot of times there's no way of getting out of work, there's no way of getting out of the calculations. It's just kind of, pick your poison in terms of which ones that you want to do. Okay. So for me, I hate doing cross products with a burning passion, and so I'm going to avoid doing that as much as possible. So I'm going to sum the moments around the center of the mass. Okay. Summing the moments around the center of the mass also gets rid of the m1g as well. So, we don't have to worry about that in the moment equation. Okay. All right. So first thing I'm going to add here are going to be the contributions from the point moments. Okay. And so the way point moments work is that, they can be applied anywhere on the model itself. And so they all just make the same contribution to the moment equation. Okay. And so first we have the point moment that's being contributed from the ankle. So that's just a T1 by itself. And then we have the point moment that's being contributed to by the knee, which is T2, but it's going in the negative direction. It's going in the clockwise direction. Okay. So that's why we have a minus T2. Right. So these are the contributions from the point moments. Okay. All right. Now we have the contributions from each of the joint reaction forces. Okay. So we actually need a little bit more information here. Okay. We're going to pull some information from our joint kinematics because we need to get some moment arms from this one. Okay. So one piece of information that we need here is we need to know the joint angle at this given time. Okay. So I'm going to call this theta 1, okay? Or we'll call it theta A just to be consistent. Okay. So theta A, this is the ankle joint angle. Okay. We know this quantity, and so this is given to us from our motion study, from our human motion kinematics. Okay. And what's interesting here is that it actually changes with time, right? And so because this person is going through a squat motion, this angle here is actually going to change with time. Okay. We don't know exactly how it's going to change with time. And so at this stage, it's not that important. And so we're just going to leave it as a generic kind of variable in our equations. Okay. Okay. And so with that out of the way, let's go ahead and compute the contributions to the moment here. Okay. All right. First thing we have, I think the easiest one to do is going to be FAY. Okay. So actually, let me go ahead and draw kind of a figure here just to make it a bit easier to see. Okay. So here we have the center of mass. Here we have FAY. Okay. And we know this angle here, which is theta A. Okay. Okay. And so to get the moment contribution from FAY, we need to multiply the magnitude of the force FAY by the moment arm between that location and M1, okay? And so since it's a vertical force, the moment arm for this force here is going to be this horizontal distance here, okay? And so that horizontal distance, we're going to use a little bit of trigonometry, okay? And so one thing that we can say is that this angle right here is 180 minus theta A, okay? Right? And so if we know that angle there, and we know this distance, right? We know this distance here is R1, okay? Then we know that the moment the contribution from FAY is going to be FAY multiplied by R1, okay? Multiplied by cosine of this angle, so cosine of 180 minus theta A, okay? And then we have to determine whether it's going to be a positive contribution or a negative contribution, okay? So based on this diagram here, we can see that FAY, if we kind of trace that around the center of mass there, it's rotating counterclockwise around that center of mass. And so that means that our moment contribution here is going to be positive, okay? All right, any questions on how we obtained that? Okay, good. Okay, so we can do the same thing for FAX, okay? And so FAX, let me just draw on the same figure here. Okay, so for FAX, we know FAX is going in this direction, right? So FAX is going in this direction right here. Okay. And so the distance that we want for the moment arm is going to be this distance right here. Okay. So the angle for this contribution is once again 180 minus theta A. Okay. We can see that it also produces a counterclockwise moment here, so it's going to be positive. Okay. So we have positive FAX multiplied by R1 sine of 180 minus theta A. Okay. Okay. And then we're going to need to do the same thing for the two forces at the knee joint as well. Okay. Okay. But for the knee joint, let's go back up to the figure here. Our triangle is actually going to be reversed. Okay. So now we're kind of coming up on this side here. Okay. So let me go ahead and draw another triangle here. Now M1 is down here. Okay. Once again, we have theta 1 here, or theta A. This angle right here is 180 minus theta A. Okay. We have FA or FKY going down, actually. I apologize. Okay. We have FAY going down, and then FA or FKX going to the left. Okay. I apologize. I'm just going a little bit fast just to make sure we get this in before we leave, just because it's going to be a week before I see you guys again. Okay, you have to be a little bit careful here. So the distance in between the knee joint and the center of mass is going to be L1 minus R1. Okay, but we can do the same thing here. Okay. And so we can get the contribution from FKY, and so we have FKY multiplied by L1 minus R1. Okay, multiplied by cosine of 180 minus theta A. Okay. that is going to produce a counterclockwise moment. So that's again going to be a positive contribution there. Okay. And then we have the same thing for FKX. So we have FKX multiplied by L1 minus R1 multiplied by sine of 180 minus theta A. Okay. All right, so it's a little bit sloppy here, but that is the moment equation there. Okay. And then our reward for doing that is a very simple right-hand side. And so right-hand side here is just going to be the moment of inertia multiplied by the angular acceleration. Okay. All right. Any questions on how we got this equation here? Okay. All right. And so we'll pick this up on Wednesdays. Remember, Monday is a holiday. So I won't be here. I mean, you're free to come here. It's just, the door will probably be locked. So next time I see you guys will be next Wednesday. So hope you guys have a good long weekend. Hope you guys rest up well, and I will see you guys next week. See you guys. See you next week. See you, Josh.